Okay, so if you're watching this at a later date, what you missed, because I forgot to press record, was I read over page 350 and 351. So maybe stop now and go do that. There's also a couple of homework problems, but maybe that should be the penalty for not showing up for 0, and I don't record the homework problems when we go over. Anyway, the definition of the area of a plane region. So like, it's kind of like blah, 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 which is all the stuff we're not going to write. The stuff we are going to write is that the area A is equal to the limit as n approaches infinity of the sum from 1 to n of f of c sub I times delta x. And there's 2 ways we can do this. We're going to write it twice. So this one's for c sub I being the minimum value on the ith subinterval. We're going to know that we're doing that if they say the word inscribed, or if I say the left-handed. Or we can define A to look like the limit as n approaches infinity, same sum from 1 to n of f of, call it d sub I times delta x. But in this definition, we would allow d sub I to be the maximum value on the ith subinterval. Which you would be tipped off to if the word circumscribed is used. Or if I tell you right hand. The left hand, right hand stuff becomes a little less accurate if it's not increasing or decreasing the whole time, which we'll see eventually. You guys can turn the other light off if you want. Give it a try. Give it a try. See if it helps. Yeah, a little bit. Okay. So plain English. Because sometimes that's helpful. Set up the appropriate Riemann sum meaning left or right-handed. And see what happens as the number of rectangles becomes infinite. And that's what these somewhat scary looking formulas mean.
So there's two things going on in each of these. And that's how I'm going to have us kind of approach these. Is the first thing that we're looking at is a Riemann sum, okay? Where we're looking at a sum of the areas of rectangles. Okay, this is what we were doing in those notes that weren't part of the text. These are Riemann sums. And then this part here, the limit as n goes to infinity, is turning the volume up to infinity. Okay. So that actually might be somewhat useful to write. This is the Riemann sum. And this is, how does this work? Turn up to infinity. It really, I think, will be beneficial as we start to do these to think of these as two separate processes. Setting up the Riemann sum and then applying the limit. Not as one big, scary, hard to decipher thing. It's just two things. Okay, so we've got 25 minutes. Will that be enough time? Well, it will certainly be enough time to get started. Yeah, let's start. I'm actually going to start this on a new page because I'll make sure it's all on one page. Okay, so this will be example 3. We will see exactly how this works in practice. Example 3. It says to find the area of the region bounded by what? By the curve y equals x squared. The x-axis and the line x equals 3 using inscribed. On your homework, it's not going to give it to you in all capital letters, but that's kind of the key word here, using inscribed rectangles. That's going to tell us that we are using the minimum values as we set up our rectangles. Especially as this goes deeper and deeper into the chapter, where we start looking at volumes, the power of a picture is paramount. I wasn't going to say paramount, but never miss an opportunity for some alliteration. It's very important to draw pictures, okay? So we're going to start this with a picture where we try as carefully as possible to label these subintervals and just everything that's going on. So let's do that. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that'll work. There's my y-axis. There's my x-axis. Wider there. 1, 2, 3. Yeah, we'll go pretty even Stevens here. Maybe go 2 centimeters. Yeah, actually, why not? 1, 2, 3. There's 1, there's 2, there's 3.
There's our 0, 0. There's 1, 1. There's 2, 4. And there is 3, 9. We sort of a flatter parabola. So we spaced out the x values. There's our curve. Y equals x squared. And we're going to drop down this vertical line. There's 3, 9. There's 0, 0. And we want to know what is the area under this curve using inscribed rectangles. Okay, well, let's set up our x sub 0 and our x sub n. So our x naught is going to be at 0, also which corresponds to a. So a is equal to 0, which is also equal to x naught. And then b is 3, which is also x sub n. And so then we're going to break this into a bunch of different rectangles. And so we're going to use regular intervals. So all of the bases will be the same. So our, how do we want to do this? We're going to start from this end anyway, actually, just because it's a little more space. So we would have x sub n minus 1 here. So we'd have f of x sub n minus 1. And we just keep kind of breaking this down. Starting from the left end, our first x sub 1, this distance here between x sub naught and x sub 1 would be delta x, which would be the same from x sub n minus 1 to x sub n. We have this consistent delta x. And so what I want to do is draw in just somewhere in the middle an arbitrary interval that we will call the ith subinterval. The ith subinterval. So we just choose some number here or some location to be x sub I. Then the one immediately preceding it would be x sub I minus 1. This base here is still delta x. And then we've got two function values here. We've got f of x sub I minus 1 and f of x sub I. So on this rectangle that we would draw here, since we want the inscribed rectangles, this ith random rectangle, given the choice between these 2 points, for this entire rectangle, we're going to be choosing this left-handed point, this f of x sub I minus 1, to draw our rectangle. And that would start from the very first rectangle, and it would go all the way to our final nth rectangle. We're always choosing this minimum value,
which in this case will always be the left hand of our interval. Okay, so there's the picture. And we will continue to flip back to the picture to sort of gain some understanding as we build our Riemann sum. Okay. So underneath here, let's set up A.
A is going to be this jacked up to infinity Riemann sum, which is going to be the limit as n goes to infinity of the sum from 1 to n. Well, what is it the sum of? The sum of these individual areas of these rectangles. Well, the sum of any rectangle is base times height. We're going to start there. Never lose sight of the fact that all we're doing is base times height. We're just doing it infinite number of times. Well, for our rectangles, let's think about what the base and the height are. The base is easy. The base of all these rectangles is exactly the same. It's delta x. The height, we're going to leave as h for now, but the base is just delta x. Okay. So now we need to make a call on what is the height of each of these rectangles, which is where this hopefully neat and careful diagram will help us. That because this is our inscribed method, the height of each one of these rectangles will always be the left-handed side. Okay? And so even starting from this first rectangle, from 0 to x sub 1, so the first rectangle, the minimum value is going to be x sub naught. Anywhere on this rectangle, the second rectangle, on this interval between x sub 1 to x sub 2, the height is x sub 1. And actually, let's do this off to the side, because I think seeing this pattern emerge is actually crucially important. And we're definitely not going to get through this example, but that's fine. Okay. Maybe just off to the side of your diagram, let's just start writing down the height of our rectangles. So our first rectangle. Will have a height of f of x naught, which in this case is 0. That's not a very interesting rectangle. This second rectangle will have a height of f of x sub 1, because we're choosing this minimum value. If we were to draw a third rectangle, what would the height of the third rectangle be? So we got our flat, non-existent first triangle, rectangle. Here's our second, here's our third. What's the height on this guy?
F of x sub 2.
X sub 2. F of x sub 2. Okay. Let's go dot, dot, dot. I think we're starting to maybe see this pattern. What would the ith, some arbitrary random rectangle, what would the height of the ith rectangle need to be?
F of I minus 1.
F of x sub I minus 1. And then just continuing that all the way, if we had the n minus first, this would be f of x sub n minus 2. And our final rectangle, the nth rectangle, this guy has a height of f of x sub n minus 1. So hopefully seeing this, you will now feel less resistance to this next line where I claim that this limit is of the sum from 1 to n of delta x, which is our agreed upon consistent base, but the height here is going to be f of x sub I minus 1. Wherever we are in this sum, whether I is 1 or 17, the height of that 17th triangle will actually be f of x sub 16. Okay, it's always going to be the left-handed side. That will change when we're doing circumscribed, okay, which we will definitely not get to today. When we're doing the right-handed sums, it'll just be f of x sub I, okay? But I need us to be at least not totally bamboozled by why it's x sub I minus 1. Maybe you're still a little hesitant, but that makes some sort of sense. And this pattern should hopefully enforce that. Okay, I'm trying to figure out where we're going to have a stopping point. Oh, I know how we're going to do this. Yeah, this will work. This will work. So we're going to get to a certain point in this example, and then basically your homework is going to be to try to finish it. Okay? So let's consider, from a functional standpoint, what is the ith input here? Okay. So what does it mean to be x sub I minus 1? Well, so what that means is for any of our rectangles, like we want to turn this into something we can actually operate on, that we can actually do this sum on. And so here's how we're going to do this. The limit as n approaches infinity of the sum from 1 to n of f.
President-elect Biden just arrived at the Capitol.
What's that?
Oh, my mic's on, my bad. Sorry, I was talking to my sister.
Oh.
My bad.
So what are these actual x values though? Like it's one thing to say, oh, I want the x sub I minus first thing, but in actual relation to the problem we're looking at, how do we get there at each stop along this Riemann sum? Well, where does this thing start? What x value? 0. Okay. And our very first rectangle, I claimed, was going to have f of 0 as its height. To get to our second rectangle height, what's the difference? How do we move from 0 to x sub 1? Delta x. So we're going to be adding, leave a little gap here because there's, and again, it'll be a little bit different with our circumscribed. We're going to be adding a delta x
to get to each successive rectangle, or the location of where the height of that rectangle is. So we're going to somehow have, okay, a new delta x, a new delta x, keep adding delta x's, which tells us we're probably going to be multiplying by I, okay, that we want for our 15th delta x, or for our 15th stop, it's going to be 15 delta x's from 0, okay? But if we just did an I here, if we just said, okay, whatever stop you're at, just add I delta x's, does that work for our first rectangle? When I is equal to 1, our very first rectangle, what is the actual function value we want for our height? Because this one right here, if we plug in a 1, would be f of 0 plus 1 delta x. 1 delta x gets us to f of x sub 1 for that first stop. Did we want f of x sub 1 for that first stop? What do we want? X of 0. So instead of using I here, we need to use, and I'll just rewrite this whole step. This is going to be I minus 1. I minus 1. Okay, so this is going to be the limit as n approaches infinity of the sum from 1 to n of f of 0 plus I minus 1 delta x's. Sorry, there's still this delta x out here for the base. This is still just the height. And now we're multiplying times delta x. And now this is going to get actually fun. But then simplifying this, oh boy, the limit as n approaches infinity of the sum from 1 to n of f. I'm going to just take away the 0. We'll see that if our sum, or if our area starts somewhere on our x-axis other than 0, this will be a number. This will be 1 or 3. This is our starting point. But in this case, it just goes away, and we have I minus 1 times delta x. This is our input, and then still being multiplied by delta x. Well, what's f? F is x squared. Oh, Mr. Smith, you're telling me we're going to have to square this? Yeah. Okay. So we're almost getting to the point where I can send you off into the wilderness. So the limit as n approaches infinity of the sum from 1 to n of I minus 1 times delta x, whole thing squared, times delta x. Where do we want to stop? Where do we want to stop? Not quite yet. So expanding this out a little bit, we get the limit as n approaches infinity of the sum from 1 to n. I'm going to do a couple things at once. I'm going to apply this square to this binomial and make it I squared minus 2i plus 1. I'm then going to apply it to the delta x, which is going to make it delta x squared, but then multiplying by this delta x, that gives us delta x cubed. And then this is right about where I'm going to let you guys see if you can do your magic. The one last thing that you need to keep in mind is that delta x, because we're defining it to be an even subinterval, is b minus a divided by n.
Well, our b is 3 and our a is 0. And so delta x here is 3 over n, which means that delta x cubed is 27 over n cubed.
So for your homework, if you don't get it done, that's fine. We'll start here tomorrow. I want you to see homework. Finish this limit. Which limit? The limit as n goes to infinity of the sum from 1 to n of what is it? I squared minus 2i plus 1 times 27 over n squared. All right, thanks for sticking with it, and we will see you mañana.
Thanks, Mr. Smith.
Yes.
How come we squared the I minus 1 delta x?
Hold up, Luke. What's that?
How come we squared the I minus 1 delta x?
Because that's what f is. So f of whatever, our function here is y equals x squared. It's all based on what the curve is.
Thank you.
Yep. Okay.